Hello, Calc 3. This is my video talking about the higher dimensional versions of Green's theorem. And so we're going to talk about the two theorems, Stokes' theorem and Divergence theorem. And so Stokes' theorem is the higher dimensional version of Green's circulation form. And remember, the Green circulation form was saying that if you do a circulation or a work integral on a closed loop, and so if you have a closed loop and you do that work integral, then instead of doing that, you can do the double integral of over the region that it encloses of the curl of your vector field dotted with a normal vector. And this normal vector, normally we don't put that there. That this form, when you actually do this, is that del G del whatever. It's like where you take the difference of those things. But this is another way you could write that. And then Stokes' theorem is essentially saying the same thing. But the idea, like I said before, it's like you take this picture and you kind of blow it up like you're blowing a balloon. And now the idea is that the integral of this closed loop in 3 dimensions, the integral of that line integral, which is, you can do a 3-dimensional line integral. We don't know if we ever did them, but you could do it the same way as we do the other ones. Instead of doing that, you could do a flux integral where the flux, you take the flux of the curl of your vector field through the normal vector. And so S is any surface that has boundary curve C. And so when I say a surface has boundary, I mean, I'm not talking about the bottom. So the bottom is not part of the surface. It's just the top part of this bubble. And the end of that bubble is kind of this circle. And so this is not a closed surface because it's kind of just the top part. And so this is what Stokes' theorem is. One thing that needs to be said about this is that there's an orientation that needs to be kind of preserved. So here, the orientation is like this is considered positive orientation. And then over here, the orientation on the surface has to match the orientation on the curve using the right-hand rule. And so if you follow the curve, so follow it around, then your thumb will point in the form that's outward facing normal. And so the orientation on surface follows the right-hand rule, follows the right-hand rule. Hand rule. And so here is Stokes' theorem. So Stokes' theorem says that if you have S be an oriented surface in R3, orientation meaning that if you take its boundary and you go the counterclockwise way, then the outward facing normal uses the right-hand rule. And you have a piecewise smooth closed boundary curve whose orientation is consistent, meaning that they match the right-hand rule. Then if you have a vector field, F, with 3 components, F, G, and H, then the integral of the work done to go along that closed curve C is equal to instead doing the flux integral of the curl of the vector field dotted with the normal vector. And so this is just a flux surface integral. And the idea is that this actually goes both ways. So sometimes this will be harder, like this will be a harder thing to do. And so we can instead do a line integral. And sometimes the line integral will be kind of hard to do, and it's easier to do a flux integral. And so you can use it both ways, but because we just don't have a lot of time, I'm going to mostly use it just using it going this way. But we will mostly use it. We will mostly use it going this way. So i.e. use a flux integral to compute difficult line integrals. Difficult line integrals. And so that's what we're going to do, although you can do it the other way. And the nice thing about this is this closed curve C, there could be actually lots of different surfaces that have that same boundary. So for instance, S is one, but also if I kind of deformed S and like have this kind of bumpy surface, that would still have the same flux because the flux only depends on what's happening on the boundary. So it's kind of cool the way that it works. It kind of a lot of canceling out kind of happens. And so that's something that's kind of useful, but again, just because of time, we can't do it. And so I'm just going to do the one type of example that I will for sure ask you. And so I'm going to start this one. I'm going to put one that looks almost identical to this on the final. And so this is a classic Stokes theorem problem. So here's the setup. You have some vector field, z, negative z, x squared minus y squared. So that's our vector field. And we want to compute the work done along that vector field if I travel along this curve C. So C starts, actually it doesn't really matter because it's a closed loop, but it's just this closed loop right here. And the idea is that if I were to actually try and compute that work integral, that would require me to parameterize 3 different lines. And then I'd have to compute a line integral on all 3, and it would just be a pain in the butt. And so computing this closed surface integral, so closed loop integral f dot dr would require 3 separate parameterizations. And that's just too hard. So too hard. So use Stokes' theorem. So use Stokes. And so I don't know, I put the apostrophe s there. So what is Stokes' theorem? So Stokes' theorem says that instead of doing the integral of the vector field f on the closed curve dr, you can instead do a double integral over a surface whose boundary is S, and then you take the curl of the vector field. So the curl of the vector field is this. You take the cross product of the Laplacian or whatever, the gradient operator, del operator, and then you dot that with the normal vector ds. And so this might not seem like it could be much easier because this is a surface integral, this is the line integral, but this line integral, because it requires 3 parameterizations, is going to be tough. And the curl of the vector field actually might be nicer than the vector field itself. And so that's why this one could be helpful. And so let's do it. And so the surface S is going to be this part of the plane, this little triangle in the plane that is bounded by the curve C. That's going to be our surface S. And so we need a parameterization for that surface S. And so S is the curve, or is the surface, Z equals 8 minus 4x minus 2y. That was what they gave us. They just gave us that plane equation. And so the idea is when you have an explicit function like that, you actually can do and I did this at the end of the last video, you can actually do a flux integral relatively easily, but we need to compute the curl of our vector field. And so this is our surface. So this is explicit. This is explicit, so i.e. not a parameterized version. This is explicit form. And so given the explicit form, we can use this formula. And so we'll plug that formula in a sec, but let's get the curl of our vector field first. So first, let's compute the curl of our vector field f. So the curl of our vector field f, remember, is I, j, k. And then you put the 3 components. So z, negative z, x squared minus y squared. And then we're going to do, oh, sorry, those are supposed to go down here. Those are the components. We put the del operators, del x, del y, del z. And then we take the mixed partial, or the partials, and so it would be that one by that one. And so the partial with respect to y is going to be, what is the partial with respect to y? It'll be minus 2y, and then the partial with respect to z is minus 1. And then we're going to cross out his column and his row, and you get the partial with respect to x of that, which is 2x. And the partial with respect to z of that is 1. And so it's going to be negative 2x minus 1. And then finally, taking the partial of that, canceling out that and that gives me 0, 0. And so it has 0 in this component. So that's our curl. And so that's not too bad. Let me make sure this is correct. If I do that, I get x squared, and then this one becomes minus 1. Oh, this one should be plus 1. Plus 1, that's where it went wrong. Because when I cancel this and this becomes, or sorry, this one and this one, it becomes negative 2y, and then minus minus, so that should have been plus. Okay. So it's going to be 2y, negative 2y plus 1, negative 2x plus 1, 0. So that's the curl of our vector field. And then we just plug it into this bad boy right here. And so what is it? So the double integral over our region S of the curl of f dotted with a normal vector n ds is equal to, we integrate over r, where r is the projection of our surface into the xy plane, collapse it all down. And then what are we integrating? We're taking this guy and dotting it with the normal vector. And so the normal vector is really, it will become this. And so the normal vector is negative zx, negative zy1. And so that's where that comes from. And that was from the other video too. The normal vector for an explicit representation is negative zx, negative zy1. And so dotting this guy with this guy requires us to compute what negative zx and negative zy are. But here's z, and so that's not that hard. And so negative zx will be, if you take the partial with respect to x, is negative 4, and so it's negative negative 4, so it's 4. You take the partial with respect to y, it's negative 2, so it's negative that 2, and then the partial, and then you just put 1. And so I dot this vector with this vector, and what am I going to get? I will get 4 times negative 2y plus 1 plus 2 times negative 2x plus 1, and then plus 0 dA. And so now we're almost ready to integrate this bad boy. And so this is going to integrate over r of negative 8y plus 4 minus 4x plus 2, so plus 6. And then let's do dA. And then I need to draw what the region R is. The way I can draw what the region R is set z equal to 0 and then graph this region. And so this is 8 minus 4x minus 2y equals 0. Or y equals 4 minus 2x. I believe that's right. And so if you plug in 0 for x, you get 4 and then 2. And so it's going to look like this. This is our region R. And so I can rewrite this as an integral. Let's do x slices from 0 to 2. And then y slices will go from 0 to 4 minus 2x. And then it's minus 8y minus 4x minus 4x plus 6 dy dx. So it becomes negative 4, what is that? Negative 4y squared minus 4xy plus 6y evaluated from, I'm running out of room. I have to add a page here. Let's just move this down here. Minus 4y squared. This is evaluated from 0 to 2. And then it's evaluated from 0 to 4 minus 2x dx. Plug that in, you get minus 4 minus 2x squared minus 4x times 4 minus 2x, and then plus 6 times 4 minus 2x. Minus, and then if you plug in 0. And so it's the integral of this from 0 to 2 dx. Then I have to FOIL this all out, and I'll get minus 4x, or 4x squared times minus 4 is minus 16x squared. And then that times that is minus 8x, and I get 2 of them, so it's minus 16x, and then minus 4 would be 16 times 4 is plus 64x. I think that's right. 8 times 8, yeah, plus 64x. And then it'll be 4 times 4 times 4, which is also minus 64. I think that's right. Let's think about that for a second. Yes, I believe that is correct. And then it will be minus 16x plus 8x squared plus 24 minus 12x dx. Oof, it's long. If I do the one on the exam, I'm probably just not going to have you finish it. Or if it is finishable, it's going to be much simpler than this because this one's a pain in the butt. So what does this end up being? I think I get minus 8x squared. How many x's do I have? Minus 28x plus 64x. So plus 36x. 28 plus 36. Yeah. And then minus 64 plus 24 gives me minus 40. Divided from 0 to 2 dx. Okay, now we're ready to plug it in. So it's minus 8/3 x cubed plus 18x squared minus 40x divided from 0 to 2. The final answer would be minus 8/3 times 8 plus 18 times 4 minus 40 times 2. That's the final answer. I have no idea what that is. I wonder if I wrote it down in the other one. So my other one, did I actually write it down? Let's see. Did I write it down? Minus 88/3 is the answer. Minus 88/3, is that the answer? Is that the same thing that I got? Yeah, it looks the same. So it's minus, which equals minus 88/3. So what is that telling us? That's telling us that the work done with this orientation is going the wrong way. And so the flux going through here is um, negative because the orientation. So I guess what does that tell us? That tells us that the vector field is probably going the opposite direction a lot. And so it's actually doing negative work as we go around in that direction. So that's interesting. Yeah, so this tells us that the net circulation is just negative, and so it's going in the clockwise direction, not the counterclockwise. So it's going actually like this. That's how it's mostly circulating. And so yeah, and so Stokes' theorem allows us to do that. And so there's a lot of good stuff in here. There's flux integrals, there's parameterizing. Well, actually, you don't really have to parameterize anything. And so I really like this one. And so this is a good problem. All right, let's end our time by talking about divergence theorem, which is the higher dimensional version of Green's flux form of uh, Green's theorem. So a reminder of what Green's theorem is for flux integrals. If you have a closed loop C and some region R that it encloses, then if you want to figure out what the flux going through that closed, excuse me, what the flux going through that closed curve is, you can instead integrate the double integral over this region of the divergence of your vector field. It's the same thing now, but what you can kind of imagine happening is if this is like a balloon, then you're kind of pumping up the balloon. And now the boundary of your balloon actually becomes the whole surface. And then the interior of that is the domain D, or the three-dimensional region. And so divergence theorem is actually a higher dimensional theorem. Stokes' theorem is kind of a two-dimensional theorem, I would say, because it has to do with a surface, and you're taking an integral of a surface, and so that's a two-dimensional object. Whereas divergence theorem is saying you're taking the boundary of a three-dimensional object, and the boundary of a three-dimensional object is a surface. And so it's kind of going from 2 to 3 dimensions. That's why it goes from a double to a triple integral. And so that's how you know when it's a divergence theorem problem, because you're dealing with a volume. There's somehow you're enclosing a whole region, and so the volume is important in this case. And so what divergence theorem says is that if you have a vector field, then the double integral of the flux integral through a surface, a closed surface, so meaning a surface that encloses a whole three-dimensional range, so there's no holes in it, it closes it, so like the surface of a sphere essentially without any punctures on it. That's a closed surface. Instead of doing the flux integral through that surface, you can instead do a triple integral on the divergence of the vector field over the domain D that it's enclosing, and N here is just the outward facing normal. So if you enclose a region, the outward facing normal is the one that's on the outside of the surface. And so the reason why the divergence theorem is so nice is because so often the divergence of a vector field is way nicer. And so I'm going to give a couple examples of this one because a lot of them actually not that hard to do. So consider the rotation vector field given by negative y, x minus zy, and let S be the hemisphere x squared plus y squared plus z squared equals a squared together with its base. So it's a closed region. So the idea is you have this kind of base at the bottom that has radius a, and then you take the dome on top of it. And so you kind of have this, I don't know, this is a horrible picture, but you get the idea. Um, maybe something like that. So it's this closed dome that you have, and it has radius A, and we want to find the flux of this vector field right here across S. And so in order to do that, if we actually wanted to compute this integral, because it includes the bottom, we would have to figure out, we'd have to actually do two surface integrals, where I call this surface 1, and then maybe the bottom surface is surface 2. And so then the double integral over the surface S, and we call it a closed surface because it closes the region just like a closed loop closes a loop, um, of f dot n ds we'd have to do two surface integrals. We'd have to do over S1 of the vector field dot n ds plus the double integral over S2 f dot n ds. And so in order to do the flux of this whole thing, we have to compute two different integrals, and that's a pain in the butt. And so divergence theorem makes it way easier. So let's compute the divergence of our vector field f. And the divergence of our vector field f is take the partial of that with respect to x, that with respect to y, and that with respect to z. And it just equals 0. It's 0 plus 0 plus 0. And so therefore, the double integral over the surface S of f dot n ds by the divergence theorem is just equal to the triple integral over the enclosed region D of 0 dv. But that's just 0. And so without doing any real work, we're able to show that this flux would be 0. So there's no net escaping from this because it's a rotation field. And so that makes sense, right? It's kind of rotating around. Things aren't actually escaping out of the hemisphere. Let's do a slightly more interesting one. So computing the flux with divergence theorem, let's say we have this vector field given by x, y, z times 1, 1, 1. And so the idea is that at every point on the surface, you have some kind of vector radially pointing out. I guess it's always really pointing in that direction. It's always pointing in the 1, 1, 1 direction, but then its magnitude is given by the product of x, y, and z. And so as long as we're positive, it's always going to be pointing up and to the right. And the idea is that if I wanted to compute the flux, the outward-facing flux across the boundary of the entire cube, I would have to compute the flux out of 6 different surfaces. So if I wanted to compute this double integral of S f dot n ds, I would have to do the integral over 6 boundary surfaces. Double integral. I'd have to compute the double integral over S 1 of f dot n ds plus dot 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 plus I'd have to do it for 6 surfaces. S6 f dot n ds. So for each boundary piece, boundary surface, because there's six boundary pieces on a cube, and so that's a pain in the butt. That would be horrific. Even though 3 of them are going to be 0 because x, y, and z are 0 on those ones, and so you'd really only have to do it for 3 of them. But still, it's a major pain in the butt. So instead, let's use the divergence theorem. So let's compute the divergence of our vector field. The divergence of our vector field in this case will be take the partial with respect to x, it's yz, plus the partial with respect to y is xz, plus the partial with respect to z is xy. So that's the divergence of our vector field. And then we just triple integral over the unit cube, d, which is the unit cube, that vector field. Or now it's not a vector field anymore, sorry, that scalar function, because the divergence gives us a scalar function, dv. And so that's, I mean, not easy, but not hard. We just integrate from 0 to 1 because it's just a unit cube, 0, 1, 0, 1, 0, 1. And then it's yz plus xz plus xy d. It doesn't really matter what order we do it in. And then we just start doing it. And so the integral with respect to x would give you xyz, x squared z over 2 plus x squared y over 2, evaluated from 0 to 1. And then I got to do the double integral for dy dz. So what is that? If you plug in 1, you get yz plus 1/2 z plus 1/2 y dy dz. Integral from 0 to 1, 0, 1. Integral with respect to y, we get y squared z over 2 plus 1/2 yz plus 1/4 y squared, evaluated from 0 to 1, dz, from 0 to 1. Whatever the heck that ends up equaling, that will be 1/2 z plus 1/2 z plus 1/4. Integral from 0 to 1 dz. And so that will be z squared over 2 plus 1/4 z evaluated from 0 to 1. And so our final answer is just 3/4. And so that is the net flux going out of the box, which makes sense that it's positive because they're kind of pointing out. And so this represents how much is escaping the box in total. And it's equal to the divergence of our vector field over the triple integral. And so that's nice. And it can actually get even nicer. There are instances where the divergence is so nice that you can do even simpler things than this. And so here's an example. This looks like a really, really complicated vector field. But the thing is, the divergence of it is not complicated. And so we're going to take the flux of this surface integral, or this vector field, over S being the surface of a sphere with radius 3. And we're going to compute the closed kind of flux integral through that surface. And so what are we going to do? We're going to use the divergence theorem. And so the divergence of our vector field F is actually going to be a constant. It's going to be 2 plus 1. And then if you take respect to z, it's plus 2. And so our divergence is just a constant, which means that this double integral, this surface integral, S of f dot n ds, is actually just equal to a triple integral over the volume d, or the kind of enclosed three-dimensional space, of a constant dv. But then that's just 5 times a triple integral over d of 1 dv. This is the volume of d, which is a ball of radius 3. And so this is equal to 5 times 4/3 pi, and the radius was 3 cubed. And so whatever the heck that is, that's 9 times 20. And so it's 180 pi. And so that's the total flux of that vector field. Even though it's like a really, really complicated looking vector field, its divergence is really simple. And so we can compute this. And so whenever you get a nice divergence, then these triple integrals just boil down to just volumes. And so that's a nice little hack too. Real quick, I just want to kind of talk about how all these ideas are related. They're all just higher forms of the fundamental theorem of calculus. There's kind of this through line of that. So the original fundamental theorem of calculus says that if you integrate the derivative of a function from a to b, you can just evaluate the original function f of b minus f of a. And then the fundamental theorem for line integrals said that if you integrate over a curve c, the gradient of a function, then you can just evaluate the original function f evaluated b minus a. And so the idea is it's like you can integrate something like over something, a derivative, or you can instead evaluate at the endpoints, kind of at the boundary. And that's actually what's happening with Green's theorem too. With Green's theorem, if you integrate a sort of derivative, you can instead integrate on the boundary a lower dimensional form, or the non-derivative. If this is the derivative of this guy, this is the derivative of this guy, this is kind of evaluating on a boundary. This is also like evaluating on a boundary. And that's what Stokes' theorem does too. It's saying instead of evaluating the derivative, you will, of over a surface, you can evaluate the original function on the boundary curve. And so there's this interplay between integrating over a thing, a derivative, or evaluating the non-derivative thing at the boundary. So derivative and boundary kind of switch roles. And it happens in all these kind of dimensions, and this is the divergence theorem is an even higher dimensional version. This again is the sort of derivative on a three-dimensional object, and I instead take the original function, not the derivative, over its boundary surface. And so there's this kind of through line of all this ideas of if you integrate a derivative, you can instead integrate the original thing on the boundary. And in these cases, that integrating on the boundary just means evaluating at the boundary, whereas this one, you actually have to integrate something. And so that this idea of kind of seeing this through line, this pattern is something that mathematicians love to do. And so they generalize it. And this actually happens in all kind of cases. And so it leads to what's called the generalized Stokes theorem. And so generalized Stokes theorem says that if you integrate a manifold, which is just kind of a higher dimensional version of a surface or a volume, and you do its what's called its exterior derivative. And so this is kind of a higher dimensional version of a derivative. You can instead integrate on the boundary of your manifold the original thing. And so this idea of generalized Stokes theorem, it really does take that idea and it goes further. And all of these are just special cases of this general process that really is calculus, that kind of adding up things and taking a derivative somehow related to each other. And it deals with this with stuff on the boundary. So this is a really cool idea. And so generalized Stokes theorem is a very, very deep mathematical thing where there's no way we could ever even touch it. But I wanted you to know that there is a kind of a deeper underlying principle. And so, yeah, you should have everything you need, and we'll talk about reviewing on Friday. Have a good one.